Good afternoon, good morning, and good evening, wherever you are. Welcome to OpTek's webinar, where we're going to be talking about machining where other people can't, and particularly talking about laser solutions for confined spaces. The webinar will be recorded, and there'll be opportunity at the end to ask questions. If you navigate to the question box at the top right of your screen, you'll be able to ask questions so we can curate them at the end of the session. And really looking forward to hearing some good engagement over the course of the webinar. So a little bit about myself. My name is Bruce Valentine. I've been the Global Managing Director of OpTek for over 3.5 years now. My background's in the interconnect space, so dealing with miniature connectors, cables across the wavelengths from high power to optical, and in different markets such as industrial, medical, and space and defence. We have a global business here. I'm currently based out of the Oxford, UK headquarters. We also have sites which support customers in South Carolina, Boston, and in Dongguan in China. So today we're going to talk a little bit about laser micromachining, but I wanted to say a few words about who we are and what we do. So we are a global provider of precision laser processing solutions. And when we talk about that, we mean using different types of lasers in different configurations to develop processes for customers to machine materials. And these materials can be anything from ceramics, polymers, organics. If it exists, it can be laser machined. And also our roots really start around fiber processing, so the processing optical fiber. And for those of you that aren't familiar, these are things such as single mode, multi-mode, simplex, ribbon type fibers where customers need machining of the ends, removal of cladding, or other kind of laser-based processes to help them with yield and optical performance. And after we figure out the recipe, it's quite common for us to develop modules and automated bespoke machinery for our customers, which we deliver and support on a global basis. I think the next slide really shows some examples of some of our standard laser systems. And these range from anything from a desktop type laser marker to slightly larger ribbon strippers through to standalone laser micromachining systems with 5 axis of motions and different laser sources. And indeed, the biggest machine we've ever built has been about 7 tons with 5 different laser sources with sub-micron precision. And the smallest, which we'll talk about later on today, is around about 8 millimeters in size. So hopefully that gives you a full suite of our machine portfolio and the solutions we're able to develop in conjunction with customers like yourself. I think when we think about these machines, I think it's also important to think about the industrial context in which we're talking about today. And a big thrust of the value that we're going to share with you is about how do you address challenges in maintenance and repair. And depending on your industry, they'll be slightly different, but in general, we're seeing lots of interest in people working in very confined spaces, either for people or tools, such as complex aircraft engine geometries, through to very hazardous environments, such as chemical or radioactive energy areas. There's also a lot of concerns around how you do this in an environmentally proper way, to conform with the minimum regulatory pressures, and also to protect your people. I think it goes without saying that the people in your team deserve to go home in the same condition that they arrived, and trying to understand that doing this in the right way also comes along with significant safety benefits, but also financial benefits. And I think when we look at some of the markets where our technology has been deployed on the next slide, you can kind of get a sense of how valuable this can be for you when you're thinking about using lasers in maintenance and repair. So one of the case studies that we work closely with our client was involved how do you do on-wing repairs? And to take a big engine off of a civil airliner can cost a lot of money. You know, any maintenance you do on anything, even outside of aircraft, increases the risk of maintenance associated failures, and a significant amount of money and time goes into the operational maintenance of civil airliners. So anything we can do to help that industry to make that more efficient and safer, this is what you'll learn today. moving into kind of energy, a lot of challenges are faced when a nuclear reactor comes to end of life, and it can take over 20 years to decommission a nuclear reactor. The maintenance and repair bill typically be at $50 million per year, which is right and proper. You want the nuclear facilities to be safe. And there's a lot of downtime per year due to safely reduce this. It can be reinvested elsewhere in the business. And finally, from an aerospace and defense perspective, lots of hours are spent on every flight hour for military jets, and a lot of flying days are actually lost during this process. So again, when you think about the cost per hour, this technology we're going to show you today is a really quick way to keep the aircraft flying more economically, more efficiently, and to decommission things in a way that protects your operators and can actually be very precise and targeted. And I think so. Before I introduce my colleague, I wanted to kind of give you a sense of scale. So what have we done? We've adapted all of our 25 plus years of learning about laser processing and shrunk that down into an ultra miniaturized delivery system that can be used safely and remotely in confined spaces. So this is how you can navigate curved, shielded spaces, carry out methods such as cleaning, ablation, or inspection tasks safely and precisely. And I'd like to hand over now to my colleague Mike, who'll introduce himself and to take you through the rest of the technical presentation. And I will see you again towards the end. Thank you.
Yeah, well, many thanks, Bruce, for that introduction. Yeah, just to introduce myself, I'm Mike O'Key. I'm the fiber processing manager at OpTek Systems. Been working in sort of laser processing of optical fibers for quite a few years. That's actually processing the fibers themselves for telecoms and medical markets, but also using fibers and launching laser beams down them and doing things at the other end of the fiber. I'm also involved in sort of special projects, unusual projects, and really that's what I'm going to be talking about today. So what is restricted access, and what do we think about when we think about restricted access? Well, that can be deep inside a jet engine. It can be a nuclear reactor, a complex chemical work, so the complex arrangement of pipe work. It can be on the shop floor with some difficult to access welding job or cutting job. And that they're all, it's all areas that are going to involve something of a headache in trying to gain access to those areas conventionally. So taking an aeroplane engine off a wing is very expensive, very time consuming. Diving deep into a nuclear reactor is not advisable. Again, expensive, the safety aspects of that. So we need a way of accessing these areas, remotely, which means that we can't really use the conventional techniques. So we began to look at this several years ago when a major aerospace civil engine manufacturer came to us with a particular problem to solve, where they needed to get deep inside the compressor blade region of an engine to do some repairs. So we started having a look at that for them. But first of all, before I move on to that, what are the current laser beam delivery methods? Well, sort of going from right to left here, then you've got free space delivery, which involves bouncing your laser beam off mirrors, and of course they're generally quite bulky arrangements. And then you've got articulated arms. So with this technique, you can actually move your laser beam around either on a robot or manually. The arm is a tube which has mirrors mounted in it. And then we've got fiber lasers. Fiber lasers have sort of revolutionized laser processing in the last 15 years. Not only is the laser itself, the laser beam generated inside an optical fiber, it's then launched into the outside world through an optical fiber, which enables a lot of flexibility of what you can do with that beam. But all of these methods of manipulating laser beams, they're all too big and bulky. even the fiber lasers, the actual, the standard off-the-shelf fiber laser is going to have a substantial jacket around the fiber, and then something on the end, which will be a collimator or a focusing head. These are just too big for what we want to do. We're looking for something that's going to fit within an 8mm volume, an 8mm tube. So that only really leaves us with fiber optics again, and launching our laser down a fiber optic. And a small fiber optic is going to be very flexible, but this is going to come with challenges. And what are the challenges with launching lasers down fiber optics? Well, we do know that you can get kilowatts down fiber optics. The fiber laser manufacturers do this. But for our application, that's going to involve complex launching schemes. And in general, the fibers are going to be too large. So to explain this, I just want to talk a little bit about fibers themselves. What is a fiber optic? And I'm sure most of you know, but it consists of a core and a cladding of slightly different refractive indices. And because of that difference in refractive index, light entering that core is reflected off the interface and is guided down the core. And this can go on for many kilometers. But in order for that to happen effectively, in such a way that the light is guided in the core and doesn't spill out into the cladding, then there is a parameter called the numerical aperture of the fiber. And this determines the range of angles that you need in order to launch your laser beam into the fiber. Not only do we have this numerical aperture parameter, but the core diameter is also important. And if for small core diameters, single mode fibers, this maintains very good beam quality. As your core diameter increases, then your fiber is becoming increasingly multimode, which degrades beam quality. So getting a trade-off between the core size and what you want to do at the other end and your beam quality, and your launching optics to effectively keep your beam within this numerical aperture value. The trade-off is required to do this effectively. And likewise, at the other end, the light coming out the end of the fiber is also determined by this numerical aperture parameter. In fact, it's the same. So the spread of light coming out the end of your fiber in general is the same as the the criteria for launching light into the fiber. As the light spreads from the end of the fiber, it's then got to be managed somehow. And if we're talking about using an 8mm diameter head, then this squeezes everything down. This makes the optics small. And it also means that we have to have some control over this spread of the light coming out the end of the fiber. So, as I say, it squeezes the optics down. We can't allow it to expand too much. And then we've got to be careful of damaging our optics. So we have to think about laser damage. And these are some slightly horrible images here of laser damage. On the left here, we have a laser damage of a quartz optic. And on the right, we have a damaged circuit board, a component that I'll show you later in the presentation. And this is if you get it wrong. So what we've got to ensure is that the optics are clean, and that they have good quality coatings on them. We can limit the amount of average power that we're putting down. We can limit that by duty cycling the power, and we can also introduce cooling into the system. So once we've launched the light down our fiber, we've selected our fiber to maintain good beam quality and be able to launch the amount of power that we need to be able to do materials processing. Once we've done that and we've have an arrangement of optics at the end of the fiber that can capture that light within the small radius that we want to, then we need to think about, well, how are we going to manipulate that beam? So it's not really much use coming out the end of the fiber and not being able to do anything with it. We need to be able to move that around. So what are the current techniques of moving a laser beam around? Well, first of all, we have galvanometer scanners, very widely used in the laser industry, and we use them here at OpTek and in our systems all the time. They involve using two mirrors mounted orthogonally, which will move the beam in X and Y. They can move the beam very quickly and very precisely. But galvanometer scanners generally are sort of the size of a box of tissues. The smallest ones available on the market are still too large for what we want to do. They're generally still sort of 60 millimeter cubes. So as well as galvo scanners, we can use spinning wedges or Risley prisms. Again, this is something we do at OpTek all the time when we're doing precise drilling. And the prisms on this image here are mounted in these pink circular motors, and they just give you an idea of the size of the hardware here that's required. And again, this is something just too big, too bulky. We can't use those in what we're trying to do. We also need to think about the geometry of what we're trying to do here. So, do we want the beam to come out the front, or do we want it to come out at 90 degrees to the head, or does it need to come back on itself? So, like I said, a number of years ago, this engine manufacturer came to us with this particular problem. We then worked with a MEMS manufacturer, which is a micro electromechanical system. And in a MEMS device, this is a moving mechanical system that's literally etched onto a chip. So all the moving actuators are actually etched into the silicon chip itself. And here is an image of the device that we actually use. And the mirror here is only 3 millimeters diameter. It's elliptical. It's 3 millimeters diameter across the long axis. So that gives you an idea of the scale that we're dealing with here. The selection of the mirror was also critical, and there was quite a lot of development went into that. So not only does it need to be massive enough that it can handle the laser powers that we're dealing with, it also needs to be thin enough that it can be supported on the MEMS structure underneath without breaking that structure or without affecting its performance. So in the end, we have an elliptical mirror, 3 millimeters along the long axis, but only 50 microns thick, silicon with a high reflective coating on it. And we demonstrated in excess of 50 watts average power reflected from this. So on the right, we can see a schematic of the 8 millimeter diameter head incorporating this MEMS mirror arrangement. On the right here, this is the fiber coming in, and inside here we've got collimation and focusing optics. This video here is showing the MEMS actually moving, and this is an early prototype version with a circular aluminium mirror. And we're able to get deflections of around plus or minus 5 degrees, which is sufficient for what we're trying to do. So this MEMS head was then built onto what's called an Endoflex arm, and this is a manually manipulated articulated arm. And the image on the right here shows the head and some of the arm there next to a 2-penny piece to give you an idea of scale. And we were able to demonstrate this to greater than 20 watts, 1 millijoule of nanosecond laser pulses. The head also contains, the arm also contains the control wires for the MEMS device itself and interlock wires. So all of these things are tested and developed in the laboratory environment, and here you can see the MEMS head that I've just seen on the previous slide. The orange part here is the fiber optic delivering the beam, and it's just performing a machining process there on a compressor blade. So this system was then interfaced with a bit of portable laser kit here that we can showing you on the left. There's the kit, and then on the right is the umbilical, which carries the laser fiber, the MEMS control wires, and the interlock system, up to a manually manipulated Endoflex arm. On the right, you can see that arm deployed here on a jet engine. And when it was deployed, we then show you a video of part of this is animated. This is how it's introduced into the engine. So it's got to navigate around a few corners and a few tight spaces until it gets to a final resting place between two blades. And there, I think the video will then switch to the actual footage. A bit of a simulation of the laser beam there. And then we're going to the actual footage where the engineer's introducing this into the engine. There's also a boroscope camera in there to help him guide it to the point where it needs to be. And there's the head. It'll emerge from the outer articulated segmented section. There it is in place, and there it is actually performing some materials processing on the edge of that compressor blade. And this is actually for a live engine repair to actually blend away a small crack in that blade. So I talked about that being a manually deployed system. Well, this particular technology is obviously well suited to robot deployment, and that formed a collaborative project that OpTek was involved in with the University of Nottingham, Rolls-Royce, and UKEA Race. This was called COBRA, which was Continuum Robot for Remote Applications. So this involved mounting the laser head on a continuum robot or a snake robot. And in this particular case, we had the luxury of increasing the diameter to 9 millimeters. So a 1 millimeter increase in diameter. But that did enable us then to include navigation cameras, illumination, LEDs, and even a shape sensing fiber. And that system was then incorporated into a little portable unit. And you can see here we've got the control laptop here on the left. And this contains the mechanics and the electrics of the actual the control of the continuum robot itself. We have a joystick control mechanism, and then the interface here for the engine. And this was deployed in an engine and remotely controlled from 100 miles away. So the MEMS technique is great, and it enables us to shrink things down and manipulate a laser beam in a very small format. Because of the nature of what a MEMS device is, as I said, it's etched onto a piece of silicon. Under certain circumstances, in certain deployments, it's probably not going to be terribly robust. And for that, really, we need to look at another technique. So here we looked at shrinking down the spinning wedges technology that I showed you in a previous slide, again, to sort of 8 millimeters. But initially, we shrunk this down to 12 millimeters. And so we're using now transmissive optics. So there's no stringent requirement on the performance of a mirror as such, which means now that we can potentially use higher powers. So if we use one optical wedge and we spin that wedge, we're going to transcribe just a circle. If we use two wedges and we spin them at slightly different speeds, then that circle will move in and out and change diameter, and that gives us a way of laser machining, removing material in a controlled way. And then if you can synchronize these wedges in other ways, the phasing of these wedges, then you can produce other shapes. So we took this technology and we shrunk it down here to a 12 millimeter diameter for another in-engine repair activity. And again, we have the blue rod here is the fiber coming in. And we've got two micro motors, the smallest commercially available motors that you can actually get In the center section here are some gear wheels and also mounted the optical wedges. The beam exits off a high reflector through a focusing lens and 90 degrees out the side of the device. This could be configured also for forward firing, fairly straightforward. The other thing we've got on here is a fairly rudimentary homemade encoder system. These motors are too small to have their own encoders, so we developed an encoder system using a transmit receive fiber optic that looked at rotating flags here, both for both wedges individually. And with that technique, we were then able to control the laser power. As that circle changed its diameter, we could control the laser power and synchronize the laser with the rotation of the wedges. And so here, again, tested in the laboratory, testing on a piece of sample material here, we're actually removing ceramic from a metallic surface. So this is the 12 millimeter diameter head, delivering about 20 watts of laser power to the surface here. And then what can you do with that? Well, that processing area, if you want to increase your processing area, when you can tessellate these circles, and so this is a sort of about 25 mil by 25 mil area of removed material. The cross section on the right shows you that the control we can get with this system. So this here we have the substrate material. There is an intermediate metallic layer and then the top ceramic layer. In this particular application, it was important that the ceramic was removed, but the metallic layer, this intermediate layer, was kept intact. So with this control of the laser power and other parameters, we were able to do that. And so again, this was mounted on a continuum robot up at the University of Nottingham and deployed inside a test combustion chamber. And this video just shows you that process happening. And then we've got here some other applications. So using the same bit of kit here, we have removed a sort of horrible organic substance from the inside of an aluminium container. And then on the right, we have another video of a deployment up at Tharsis Limited, again inside a jet engine there. And you can see that the even with this curved geometry, the head is here, slightly odd angle, the head is here. Even with this curved geometry, it's dealing with that and managing to remove material fairly evenly over the area that it's actually removing. So that 12 millimeter head, we were able to shrink that down further to the 8 millimeter diameter, the original requirement that was presented to us. And this shows the edge of a compressor blade where we've removed material using the spinning wedges. And the important thing is here that the surface quality is good and that we don't introduce any more stresses in that blade from a poor surface quality. And these blades have been tested and they all are to the acceptable standard. So what about further development of the spinning wedge technology? Well, we've taken it down to 8 millimeters to probably what will be pretty much the smallest size, maybe a bit smaller than that. But we can certainly scale this upwards fairly readily. So up to 25 millimeters, maybe a bit more is what we're thinking of. Anything sort of bigger than 25 millimeters is probably then getting into the regime of systems that are possibly already out there for this sort of work. So with scaling, we can scale the laser power. We can deliver more laser power down this. If we make it bigger, we can make the fiber bigger. We can make the optics bigger or avoid damage to the optics. We're looking at cooling, possibly using, we are looking at cooling using compressed air launched up to the head and cooling it that way. We're improving the control system to get better synchronization of the wedges themselves. And then other things we're looking at which apply to this and to the MEMS device, eye-safe lasers. So there's no such thing really as an eye-safe laser, but we're looking at alternative laser sources, which means that the requirements can be relaxed in terms of laser safety for where these things can be deployed. So in summary, I've talked about two techniques of manipulating laser beams within a very small volume for accessing restricted areas, restricted access applications. One of those techniques uses a MEMS system with a small mirror mounted on it. Another technique uses two rotating wedges, and that's it. Thank you for listening.
Yeah, thank you, Mike, very much for a really interesting presentation. And again, I'd like to say thank you for the last 10 years of development time from yourself and our academic and industry partners. I mean, it's very exciting to be part of this journey. I think before we get to the Q&A, I just was, put myself in the audience's shoes. Why would you think about choosing OpTek for your next system? I think aside from being specialists in laser micromachining and working in processing relatively small, so sub 300 micron size geometries in complex arrangements and components, we offer the customer that kind of roadmap from starting of in-house recipe development and sample processing, so we can help you understand, is this really going to work in your application? And from that point, we offer that pathway of outsourced manufacturing through to full machine ownership, and often integrated with a lot of automation before and after the machine. So those decades of experience developing bespoke systems, being part of a large financially stable group of the Humanitic Sensors division, allows us to take on long-term and moving the needle type applications. And finally, the businesses all have significant industry certifications. So as you'd expect, ISO 9001, we are committed to working in an environmentally responsible manner. So 14001, and recently the UK and our Chinese site achieved ISO 13485 certification for medical applications. So I think from an end-to-end point of view, we're here to help you. We're really interested in taking this technology forwards and creating value in the industries. And on that note, I'd like to offer you the chance to post any questions in chat, and Mike and I will do our very best to answer them for you. Thank you.
Yeah, thanks for that, Bruce. There are a few questions come in, so I'll just try and address those. So what is the maximum power that can be delivered, and what materials can this be used on? So the two examples I've described here are both 20 watts, but I know that they can be taken up to 50 watts of average power. So with scaling upwards, particularly with the spinning wedges technology, then we're going to be able to deliver several hundreds of watts in that particular case. Materials that can be used on, well, so obviously in the presentation that was sort of aerospace alloys, but really, any material that you can think of, it's a laser system at the end of the day. And you can machine pretty much everything with lasers. One thing that maybe I should have said in the presentation is that we are looking at different laser sources, and in particular ultra short lasers and ultraviolet lasers that will give us access to a wider range of materials. But for us to be able to do that, we're also looking at different types of fibers. Okay, so there's another question. Is there vision and laser in the same assembly? So in the COBRA system, yes, there was. So that contained two cameras, and that actually used visual odometry to actually navigate the system. In the smallest 8mm head, there is no vision because that was intended to be used in conjunction with a borescope, with a camera on a borescope, which helped to navigate the head to the correct position. But yes, we have demonstrated vision in a 9mm diameter head. So yeah, so is this system ready to deploy now? To a certain extent, yes, but obviously it is very application and very customer specific. So we can imagine that there would be a certain amount of development work would need to be done for a particular application. Another question, is there selection of laser power and positioning done manually or automatically within the system? So both really. So it's, in this particular case, the sort of the portable piece of kit I showed in the image next to the jet engine. The power was manually selected by an operator. But these are generally, as with our bigger machines, these sorts of parameters are generally rolled into recipes that are dialed up by an operator for a particular application. So someone's asked, are you able to remove the overlap in circular areas of surface ablation function? So we're hoping to be able to do that, but it's going to require better control of the spinning optics themselves. So at the moment we can't, because we don't have that level of control in order to synchronize the wedges with the beam. But we are improving that, so we should be able to produce different types of shapes and link shapes together without having too much overlap. The other thing that we can do is, with the overlap, if we do have overlap, we can actually sync the laser in those points where we're overlapping to reduce the laser power in those regions, so that we're in the overlap regions, we're removing less material. So there's another question, how is heat dissipation managed in compact laser systems operating at greater 20 watts in potentially non-ventilated spaces? Yes, that is a good question. So the way we did it on the first system that I showed, because that was effectively a non-ventilated, very confined space, in that particular case really was limiting the duty cycle of the laser. So limiting the time it was on, switching it on and then switching it off, just to allow there to be an element of cooling between the processes. And this seemed to work quite well. But one thing I did mention is that we are looking at other ways of cooling these systems, in particular using compressed air. So I think this is possibly the final question. How do MEMS mirrors compare with galvo scanners and spinning wedges in terms of speed, precision, and durability in constrained environments? Okay, so they, So because they're in constrained environments, then obviously we have to make compromises on these things. So yeah, they're not going to give you the accuracy or speed at the moment anyway of a galvo scanner. So the MEMS typically, let's say, so a galvo scanner will give you something like a repeatability of 20 microradians. I don't have a number for the MEMS, but I know that in one of our applications, it was important to maintain the diameter of, in this particular case, an ellipse. So let's say we've got a 3mm diameter ellipse. It was important to be able to maintain that that diameter to within about 10 microns, and the MEMS device, we were able to do that. With the wedges, it's not quite as good as that, and that's to do really with the drive mechanisms that we're using, having to shrink down all the gears and the drive mechanisms to the sizes that are required. But again, when we improve the feedback from these, we're hoping to improve the precision of the spinning wedge device as well. Durability, a bit early to say. So we know that the MEMS device obviously is in certain circumstances can be vulnerable to shock. So we're hoping that robot deployment will help with that, in that it won't have any sort of violent manual crashes against the insides of containers or whatever it's going into. The spinning wedge one is certainly more durable and more robust, both in terms of its mechanical durability and its power handling durability. So I think that is all the questions.
Yes, I think, Mike, we just say thanks everybody to listening.
Yes.
As I mentioned at the beginning, this will be available for download, and you're welcome to contact us via the email address here, via LinkedIn, or via our website. And we look forward to working with you on your next project. Thanks for coming.
Yeah. Thanks for listening.